Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will start talking about analysis of variance, also known as ANOVA. Let's begin. As you can imagine, we are going to use an example to illustrate the ideas behind this statistical procedure of analysis of variance. So here's the example I would like to discuss with you in this video. So it turns out that we have two samples of measurements of elasticity. And these measurements correspond to two different processes, okay? And the sample size for each of those samples is 6. So we have a total of 12 observations. And the question that we would like to answer is whether or not that data set provides evidence that there's a difference in average elasticity between the two processes. Okay, so that's our data set. Okay, 1, 2, 3, 4, 5, 6. That's coming from process 1, another 6 observations coming from process number 2. And we want to, again, we would like to see if we have any evidence that the average for these two populations are different. Okay, so how about we start constructing a statistical model, right? As you can imagine, since this is a course about linear regression, what I would like to do is set up this problem using all those ideas that we have discussed in the past, you and I, right? So let's try and see if we could use what we know about linear regression to answer this question. So let me use y1 to represent the first observation, right, coming from process 1. And I'm going to assume that process 1 has a mean mu1, right, plus some random fluctuation epsilon 1. And then I'm going to be doing the same for the other 6 observations. Since the second one comes from the same process, process 1, I'm going to be assuming that it has the same mean, but well, a different random fluctuation. So I'm going to have a total of 6 of them, right? The fifth, and one more, and then I have my first set of observations there, right, from the first sample. Now, we know that the other 6 observations, they come from a different process. So let me assume that they have a different mean. Observation number 7, 8, 9, 10, 11, and 12 let me assume that they have a different mean. mu2, it has an epsilon 7, mu2, a particular random fluctuation for the 8th observation, and so on. I'm almost done here. Okay, you guys agree? So now I have two generic 12 observations. First 6 with a mean mu1, and the last 6 with a different mean mu6, right? Now let me say something about the errors. Let me assume that the errors are normally distributed with mean 0 and variance sigma squared, and that they are independent of each other as usual, right? But then when you see this, you go, ah, interesting. So we could express this, right, like this. Y, which is 12 by 1 vector of observations. It's going to be the same as X, where X is a design matrix. See that I could have a vector, a column vector with 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0, 6 zeros, right? Make sense? Can you see that? And then the second column of my design matrix would be 0, 0, 0, 0, 0, 0, and then 6 ones. Make sense? So it would have two columns, my design matrix, 12 rows by 2 columns, and I could have a vector beta 2 by 1, and that vector beta would have mu1 and mu2 as its elements. Can you see that? Okay, so and then of course we would have that epsilon vector of random fluctuations. Make sense? So now that looks like one of our linear models, right? So now if I want to estimate mu1 and mu2, I could do that using least squares, and then if I want to do inference, I could use you know, part of the theory that we have learned together. So let's try and do that, okay? So in this case, let's go back to the question. The question is, do we have statistical evidence that there's a difference in the average elasticity between those two processes? So in terms of our model, that translates into a hypothesis test, right? So the null hypothesis would be, guess what? There is no difference between those two processes. as far as the average goes. So mu1 is equal to mu2. Okay, so let's write that down. It would be H naught, the null hypothesis, is that mu1 equals mu2. Okay. Against, the alternative is that there is a difference. So mu1 is different from mu2. Make sense? Okay, now note that that would be equivalent to the following. Let me rewrite the null and the alternative hypotheses like this. This is the same as saying if mu1 and mu2 are equal, then mu1 minus mu2 equals 0, right? And if mu1 is different from mu2, then the difference between these guys should be different from 0. Okay? Okay. But again, note that if we use this setting, if we express our problem in terms of a linear model like this, our parameters, our beta vector, looks in this case like this. It's going to be mu2, it's going to be the second element of that beta vector, and mu1 is the first element. Make sense? So, going back to what we said, we would like to use what we have learned in this linear regression course to answer that sort of question, right? So note that mu1 minus mu2 is a linear combination of the elements of that vector of parameters of those betas, right? You could express that as a linear combination of these guys, right? And we know how we can do that, right? So to be more specific, if you go to page 618 from one of our textbooks from Mathematical Statistics with Applications, right? You'll see, let me type that so you have that in mind. So if you take a look at page 618, right, from let me say just Walkerly et al. Okay, you know that if you want to test something that looks like this, if the null hypothesis is just a linear combination of your parameters, of your beta parameters, that looks like this, A transpose times beta equals some value under the null hypothesis, and that's why they use that notation, just to stress that this value here is the value of that linear combination under the null hypothesis, right? So for instance, in this case, the value of that linear combination under the null hypothesis is just 0, right? Could be a number different from 0, but anyway, in this case it's 0, and that's what they mean by this. Is the value of that linear combination under the null hypothesis. Okay, and against, if you have the alternative, well, the alternative will be, in this case, a two-sided alternative where what we have is different from that value. Okay, but also, if you take a close look at that page of from our textbook, and we actually used that pivotal quantity, that test statistic, when we talked about the derivation of prediction interval in the multiple linear regression model. Okay, so the test statistic is a t, right? Let me call it t star. And it looks like this. It's going to be A transpose beta hat minus, we want the value under the null hypothesis here, and then we're going to be dividing by the standard error. Okay, in this case the standard error is going to be S, an estimate of sigma, times the square root. Oh, this one here is the one oh, come on. I want the square root of A transpose times X transpose times X times, well, inverse times A. Okay, that's going to be your test statistic. We have two choices for step number 3, right? We could either use a p-value approach or the rejection region approach. Okay, so let me use the p-value approach. P-value, in this case the p-value is going to be 2 times the probability that a t-distribution is greater. Let me change that here. Okay, that a t-distribution is greater than the absolute value of your test statistic. And we have to multiply by 2 and use the absolute value because we have a two-sided alternative, right? Okay. So, and conclusion, if p-value is less than alpha, we reject h0. If the p-value is greater than alpha, then we fail to reject the null hypothesis, right? Conclusion, if p-value is less than alpha, reject h0. Okay, okay, so that's what we're going to be doing. Okay, let's try to implement those ideas. Well, to implement, we are going to be using R, as you can imagine, but now we have the setup of a problem. Okay, here we go. So first we need to enter all that information, our data set. Okay, so our response variable is going to be y, and what we need there is all those guys, right? So 6.1, 7.1, 7.8, 6.9, 7.6, 8.2, 9.1, 8.2, 8.6, 6.9, 7.5, and 7.9. So let me make sure that I have them all. 12, that sounds good. Okay. Now, as you can see, we will need to construct the design matrix, because we will need it to come up with that test statistic. Okay, it's part of the denominator of the test statistic. Okay, so again, from the way that we set up our problem, we can see that the design matrix is going to have 12 rows and 2 columns, and the first column is going to be 1, 1, 1, 1, 1, 1, and then 6 zeros. So let me call x1 our first column of that design matrix X, and what I'm going to be doing here is I'm going to be repeating a 1 6 times, then I'm going to combine that with repeating 0 6 times. That's going to be our first column of our design matrix. There we are. Okay, 2, 4, 6, sounds good. Now we are going to be doing something similar for the second column, but now the first 6 elements of the second column are going to be zeros, and the last 6 elements are going to be ones. So let's see if I have what I want. Yeah, that's exactly what we want. Okay, now since we are going to be carrying out matrix multiplications with these guys, with the design matrix and so on, let's make sure that R knows that these guys are matrices or vectors, which are particular cases of matrices, right? Okay, so x1 is going to be, what we want is, hey, x1 is a matrix, right? So using those numbers from x1, I want you to create a matrix with 1 column. We're going to be doing the same with x2, just to make sure that R knows that those guys are matrices or vectors. Okay, so now we want to combine those to create our design matrix. I'm going to be using capital X for the design matrix. I'm going to be pasting these, but as columns, okay? Because let me show you what these guys look like. X1, right? It's a column vector, which is exactly what we want, but we want to paste these guys as columns to create our design matrix. With cbind, I get to do that. Hey, paste those guys, but as columns, okay? So now let's see if X is what we want. It looks like what we want, right? 6 ones, then a bunch of zeros, 6 zeros, then 6 ones. It is exactly what we want. But again, we're going to make sure that R knows that X is meant to be a matrix. So 12 rows and 2 columns. Okay, it looks like what we want. Now, let's see. We want to use our theory from linear models. We're going to be estimating beta using least squares. Okay, so let's use our linear model function lm. Our response is going to be y. Our predictor x1 plus x2. Now, note that we don't want a y-intercept. There's no beta 0. If there was a beta 0 here, an intercept, we would have a column of 1s as part of our design matrix, and we don't want that. So to let R know that we don't want a y-intercept, we do this, minus 1. Hey R, I don't want a y-intercept. I don't want a beta 0. Okay, so let's see. We should only have 2 coefficients would be, and what we have there are going to be mu1 hat and mu2 hat. Okay, we only have 2 as we should. Nice. Okay, let's keep going. So it turns out that those guys are our beta hat, right? Those coefficients form our vector beta hat. Let me save that there. Now again, since we want that, we want to treat that as a vector because we're going to be doing some matrix multiplications. Let's make sure that R knows that. So matrix beta hat, number of columns just 1, so beta hat is a 2 by 1 vector, as it should be. Okay, now remember that to carry out that hypothesis test, we're going to be using that approach. It's just a linear combination of our parameters, of our betas. So we need that vector A transpose. And that A transpose is just going to be 1 minus 1, because if you do that, you end up with, A transpose times beta, where beta is going to be formed by these two guys. That would give you what you want if A transpose is 1 minus 1. Okay? So, the vector A is C, to combine those guys, 1 comma minus 1. Let's make sure that R knows that we want that guy to be treated as a vector or as a matrix. So it is exactly what we want. Now let's find the numerator of our test statistic. We want this, A transpose beta hat minus A transpose beta. But, you know, under the null hypothesis, that guy there is just 0, as we pointed out earlier. So the numerator is just going to be A transpose beta hat. So let's find that. Numerator is going to be just A transpose beta hat. And now let's find the denominator. The denominator, we said, is going to be S, or the square root of the mean square error, because that's a good estimator for sigma squared, right? Since since it is S, the one we want here is just, you know, sigma, not the variance, the standard deviation. And then times the square root of A transpose X inverse times A. Okay, that's going to be our denominator. Let's find it. So first, we know that we could get an estimator of sigma for our model. We called it mod, with that command sigma mod is going to give you the estimator of sigma using that linear model. Okay, now we are going to multiply by the square root of that quantity, A transpose times X transpose X inverse. So it's going to be A transpose times that inverse that we want, solve X transpose X, right, times the vector A. Okay, there we are. So we're almost there. So now all we need to do is compute T star as numerator divided by the denominator. Okay, so T star happens to be negative 1.6967, right? Okay, but is that small, big? How do we know? One way of knowing is, you know, computing the p-value. Okay, so the distribution of the test statistic under the null hypothesis is going to be a t-distribution with the degrees of freedom given by, you know, the denominator, which is going to be n minus k minus 1, right? Okay, so here we go. Let's find that p-value, right? So first, note that n is this, the length of our vector of observations, n, right? So that's going to be 12, of course, right? Now, I want you to be careful here. Remember that I just said the mean square error is just SSE divided by n minus k minus 1, right? But that's what we had before, because our model, right, the models that we had before had k plus 1 parameters, because we had beta 0, beta 1, blah 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 up to beta k. But in this case we don't have that y-intercept, right? We don't have that beta 0. Okay, so in this case, right, the number of degrees of, well, yeah, the degrees of freedom in the denominator are going to be just n minus 2, right? Because that's the total number of parameters that you have, of beta parameters that you have here. Make sense? So just be careful with that, and that's because in this case we don't have a y-intercept. Okay. So okay, so here we go. Let's find that critical value. Okay. So well, no, p-value, right? We're using the p-value approach. Okay. So here what we want is alpha equals 0.05. Say that it's 0.05, right? So we know, right, and we have the expression here. In this case, it's 2 times the probability that a t-distribution with the right number of degrees of freedom, in this case it would be n minus 2, right? So the probability that t-distribution with, in this case, 10 degrees of freedom is greater than the absolute value of our t star, right? Okay, so here we go. So we know that PT would give you the area to the left of T star if you have, in this case, n minus 2 degrees of freedom, okay, but that would be the area to the left of that guy, right, which is good because the area to the left of negative 1.69 is the same as the area to the right of 1.69, which would be the absolute value, right? So we just have to multiply by 2 this guy. Remember that t-distributions are symmetric, right? So that's the p-value, 12%, right? Okay, so your conclusion is that you can't reject. You fail to reject. You don't have enough evidence to claim that these two means are different, right? Okay, so that would be your conclusion. Now, let me just remind you, and we're going to talk about this in more detail later, that if you square a test statistic t, you end up with an f, right? So next time, what we're going to in the future, in the next video, what we're going to be doing is using that relationship, because it turns out that when people do analysis of variance, they use an f statistic instead of a t statistic. Okay, but it's equivalent. The thing is that with the f statistic you can generalize that to more than 2 populations when you're comparing more than 2 populations. Okay, so let me just say that here the conclusion that there is not enough evidence to claim that there is a difference in the average elasticity. Between these two processes. Okay? Because in this case, right, what we have is, in this case, p-value is greater than alpha. Therefore, we fail to reject H0. Okay. Okay. Now, just let me say something more before we finish. Note that you could do this. You have been doing this before in the past, for instance in Statistics 260, using just a plain two-sample t-test under the assumption that the variance is the same. Okay? Okay, so now just let me summarize what we did here. So we had this problem, right, initially, where the goal was comparing the means of 2 independent populations, right? And when we translated that problem, right, using our linear model setting, right, what we realized was that that question was equivalent to a hypothesis test in terms of the parameters mu1 and mu2, but we could think about them as a hypothesis test, which was a linear combination of the beta parameters of a linear regression model, right? So what we said is that we could carry out that hypothesis test using a t-test, and in the future we're going to use the fact that t-square has an f distribution to extend this procedure, and instead of comparing just two populations, we're going to be comparing 3 or more populations. Okay, but to do that we will be using an F statistic instead. But you know, it's the same 4-step procedure, usual 4-step procedure for a hypothesis test. Null hypothesis, well, state your null and alternative hypotheses, finding a test statistic, either using the p-value approach or the rejection region approach, and finally stating your conclusion. Okay, well, that's it for now. Thank you so much for watching. Please keep working hard and take care. See you next time. Bye.